Yeah, good morning, Siddharth sir.
Hey, good morning, sir.
Yeah, this is funny.
Hi, Funny.
Yeah,
Funny and everyone on the call, please
yeah,
ignore
I'm
if
the
I
friend of
say don't. Sorry,
yeah, I'm
go
the
ahead.
friend of Srinivas.
Hello,
Recent
Fanindra. Nice,
colleague.
nice meeting you.
Nice to meet you. Meet you too.
Yeah,
Yeah,
Funny
good.
and everyone else on the call. I know all of you are like so used to being called sir. Please excuse me if I don't call you sir.
Okay.
Coming from the industry, we call everyone by their first name. It's not being disrespectful. It's saying everyone's equal.
Yeah, but in my field here we will call like sir because
It's a
that's
little,
that's the
yeah,
way
that's
of
why. Yeah,
giving respect to others.
yeah, that's why. Please
No
excuse
problem.
me if I
It's
don't say.
I also call like Siddharth. No problem.
Yep, absolutely. I go by Sid. That's the easiest way.
Okay.
Yeah.
Okay.
Funny. Can you please let me know when can we get started? I'll mute
Yeah,
myself
just
until
in a
until
few
then.
minutes. Now I will introduce you to your participants. Then we'll start now.
All right. Sure. Thank you, Funny.
Yeah. Okay. Yeah, dear participants, here, good morning to all. Our today's resource person, he is an industrial person. His name is Siddharth. He is from US. Uh, Now I'll give a brief introduction about our today's resource person. He has an 8 years of experience in industry. Now, his name is Siddharth Epuri. He is a manager of analytics data science at Verisk. Now let's see here a brief introduction about him. He is an advanced analytics professional with 8 years of experience in solving business problems in a data-driven approach. Adept at applying data mining, predictive modeling, network analytics, visualization, and big data techniques on large data sets. MIS graduate from Eller College of Management and a continuous learner. He has certified from Cloudera as a developer for Apache, Hadoop, and data analytics and big data. And he has a credentials like a hands-on experience in exploratory and predictive analytics projects, competent in advanced analytics, including text analytics and unstructured data, proficient in writing and tuning SQL queries and designing logical and physical database. Enthusiastic for big data, business intelligence, and analytics. Thank you very much, Siddharth, for accepting our request and be a part of our FDP. And we are on the behalf of the Department of CSC and Patient Staff Technologies. Here we are welcoming you to the today's 2 weeks FDP program.
Thank you, Funny. Good morning, everyone. Yeah, it's a good evening for me. Coming from the, as Funny said, coming from the industry background, my policies might look a little different to what you're used to. Sorry about that, and I might actually ask you questions. Generally, when I present in a meeting room, it's more interactive than a classroom that you're mostly used to. So I might ask questions. Please be as communicative as you can be, given the circumstances. I would love to hear from you guys as well. So my name is Siddhartha, but I go by Sid. That's the easiest way. People, especially in US, can call me. So today's agenda is to give you a brief introduction about graph theory and network analytics. I actually have myself on the slide. Like I can introduce myself on the slide in a few seconds. Let me start sharing my screen. And the topic, I'm repeating the topic because from the schedule of the FTP, you might think that today is the hands-on session on machine learning. But given that I only have 2 hours today and 4 hours tomorrow, I moved the hands-on session to tomorrow so that we can continue without breaks. The graph theory and network analytics will only take a couple of hours. So I actually discussed with Srinivas Rao and then moved it to today's session. I hope it's not a big disappointment for anybody who was expected to do hands-on machine learning today. We'll be doing that tomorrow for sure. But let me tell you, the graph theory and network analytics is far more interesting than machine learning. I love it more than machine learning, but well, I do both of them. But yeah, I'm a little partial to the graph theory and network analytics. And the reason for that is you see beautiful visualizations compared to all the machine learning, which is all code and results. This is a piece where you can see like more very interesting and beautiful visualizations. Before I get started, has anyone worked on like graph theory and network analytics before, or has anyone like have an introduction to graph theory and network analytics? I'll give you a minute to respond. Any one of you, if you have experience with graph theory and network analytics, please do speak up. All right, I consider that as probably all of you are new to graph theory and network analytics. I made my slides in a way that it starts from the scratch, so that it might be a good introduction for you guys into graph theory and network analytics. So starting here, the agenda for today is that I'm going to just introduce myself, like who am I, and then we'll define like some key terms like what is graph theory, what is network analytics, and what are the like key components of it, and then some metrics that we can leverage or we can generate from graph theory and network analytics. And some of the tools, most of them are free tools. Like if anyone is interested in using this technology, these tools are free to download and explore. And then I will walk you through one example of oil network analytics. I'll start with traditional CSV file, which is a tabular data, and then we convert that data into a graph database. And then I'll show you the queries to create that graph database and to leverage the graph database to answer some of the queries for the business purpose. And then I'll also leave you with some of the other use cases that you can use graph theory for. So who am I? My name is Sid, as I said, Sid Yepuri. I have a master's degree in management information systems from Eller College of Management, University of Arizona. Just a little bit about the school is the MIS program at Eller is ranked number 3 in the entire United States, and it's ranked number 1 in the public universities. It's a very good program. I finished my master's in 2015, and then I started working as a data scientist in a company called Verisk Analytics. And from being a data scientist, I did all my hands-on work, and I have a steady career progress in the same chain. And then I became a senior data scientist and then a lead data scientist. And now I serve the company as a manager of analytics in data science. And then I have overall 10 plus years of industry experience. I worked for about 6 years in India. I was working as a database analyst, more like reporting tasks. And then after I finished my master's in US, I started working in data science area, and I've been working for more than 5 years. And my general interests are like data science, of course, is my interest, and then graph theory for sure. And then I do a little bit of photography, nature photography and wildlife photography. And then I play tennis. These are some of my interests. Introducing the graph theory. I have a quick request. Sorry to disturb, guys. Hey, funny, I see these 2 lines on the screen. Is there a way that we can get rid of those 2 lines?
It is visible, no problem. You can put.
Oh, okay. All right. So the graph theory, right? What is graph theory? I've been talking about like graph theory since the last few minutes. What is graph theory, right? Graph theory is a study of graphs. Graphs are not the plots. What we are talking about, graphs are the mathematical structures used to model pairwise relationships between objects. A graph can be a good example of a graph can be, right? If we imagine all of our connections on Facebook, in terms of like nodes and relationships, each of us will become a node, and we are friends with someone and we have a relationship with someone that becomes a relationship between two people, right? that's uh that's a digital representation of physical world connections in terms of graph. That's what a graph is. It's made of vertices, which are nodes that are points, and then it is connected by edges or links. The nodes are connected by the edges or links. That's what a graph is. And generally in computer science industry, graphs and networks are used interchangeably. The only difference, unlike if you go out of the computer science domain, the only difference is that networks are the real world graphs. So network, like the one example we're going to look at today is a network, because it shows us how all of the oil wells in the world are connected, but I'm only using the North America continent for today's example. So what it shows us is, like, all of the oil wells as nodes, and all the pipelines that are used to transport oil from one platform to the other platform, and then eventually to a processing unit, a refinery, where the crude oil will be processed and we get our petrol and diesel. So that's a real world example of like how each of the components are connected using pipelines. So those are the networks where you have a physical presence. Graphs are in general are in digital world. In computer science, networks and graphs become the same. And then some keywords in the graph theory. A node is the basic element of graph theory. Node is the, as I said, like, is an entity. Basically, a node is a representation of entity. In terms of like social networking, you can treat each person as a node. Or in terms of like our network, as I was just saying, each platform will become a node. In Twitter, each person become a node again. And then a relationship is a link between two nodes. It might contain direction in some cases, and it might not contain direction in some cases. In example of Facebook, right? If I say like I'm friends with Funny, I am friends with Funny, and Funny is friends with me. So there is no direction. Direction is not important there, because one connection implies both the people are connected, and there is no direction meaning for it. But when we go to Twitter, if I follow Funny, there is only one directional follow relationship. If I'm following Funny, it doesn't mean that Funny is also following me, right? Funny has to like explicitly follow me to say that Funny is following me. So one relationship will not mean the other relationship is also present. That's where the direction is important and the direction is present. And sometimes we have like relationships, and there are like weight that we could use for the relationship. Like, for example, if there is a page on Facebook, and you are following the page, and the number of times you liked the page posts might become the weight of the edge. It is to identify like how strongly two entities are connected. Sometimes, like, just saying friends is good enough. Sometimes, hey, say how many times you like their posts and how many times you like their photos on Facebook. That will become a property of the relationship, and that'll add more weight to the relationship. So we can add weight to the relationships as well. In simpler terms, yeah, this is what I have been talking about, right? 1, 2, 3, 4, 5, 6. These are the nodes, and the relationships are like the connections between those two. And in terms of graph theory, there are 3 different types of traversals that we can make in a graph. I'm going to just define these terms for us. A walk is an ordered alternating sequence of nodes and relationships. So basically, a walk is a random walk between any nodes in the network. And a trail is a walk in which no relationships are repeated. So in case of walk, you can use the same relationship more than once, like 1 to 2 and 2 to 1. You can do that relationship walk multiple times. But when we call it a trail, you can only pass through each node only once. Sorry, each relationship only once, I'm sorry. And then when we come to path, A path is a trail in which no nodes are repeated. So you can't even repeat the nodes and relationships. So a path is the shortest way for going from, like, let's say 1 to 5 or 1 to 6. You can only go in like one direction, 1 to 6, and only once. You can't use a separate relationship, or you can't use the same node twice. You can't use the same relationship twice. Any questions so far on the definitions? All right, I take it as no questions. Let's move on. And as I was saying, like, there are directed graphs, undirected graphs, and weighted graphs. And the mathematical representation, right? We are seeing all these visuals, but how do we use this for computationally, like, for computational purposes in programs, right? That's where the adjacency matrices come into picture. So the way of representing a graph in computer terms or in mathematical terms is by using an adjacency matrix. In case of the first adjacency matrix we are seeing on the screen, it's an undirected graph. As you can see, there is no arrow mark between like A and D, or A and D, or A and C. They are just connected to each other without any direction. So it's an undirected graph. And when we have undirected graphs, the adjacency matrix will be a I forgot what is the term for it. I'm guessing it is the reciprocity matrix, where, like, A to B is the same value as B to A, and A to C is the same value as C to A. So you can only, like, work with one triangle, or like one half of the matrix, and you still have the full representation of the matrix in terms of undirected graph. Whereas when it goes to directed graph, it's not the same, because, as I said, like in the Twitter case, if I am following someone, I am following someone, but that someone might not be following me. So if I say A is following B, or A has a directed connection to B, it means only A has a connection to B, but B may not have a connection to A. So when you're traversing using a walk or a trail or a path, you can't come back. You can only go in one direction. That is the directed graph's importance. And it's again the same thing. We represent it in a matrix where, like, a relationship is present between two nodes. We designate it with a 1. And if there is no direct connection between those two nodes, like in the example, the second example we are seeing on the screen, between A and C, there is no direct relationship. There is only one direct relationship from A to B. So A to B will become 1, and everything else is 0, because there is no other direct relationship. Whereas when it comes to B, B has direct relationships to C, D, F, and G. Again, and if you see the B row here, you will see like C, D, F, G are nominated with 1, but everything else is 0. And again, we can see this here. B to A is a 0 because it's not A to B. The direction is saying it's only A to B, it's not B to A. That's the directed graph's representation mathematically. And then in case of a weighted graph, we use the same thing. Instead of putting a 1 or 0, we use the weight of the relationship to represent the adjacency matrix. Like, for example, if you see A to E here has an edge weight of like 12. So if you see here in the matrix, A to E will be 12. Similarly, like A to F is 16, A to G is 12, the same thing again. So that's the mathematical representation of how the graphs are represented. The reason I'm showing this is, right, the graphs are, whatever we are seeing today, are visually appealing. They are visually easy to understand. But when it comes to like big data sizes and computations on big data sizes, we don't do it visually. We actually calculate using the mathematical representations of it, using like matrix and vector calculations. All right, I'm going to introduce some graph measures. Like, we build a graph, but what do we get from it, right? How is it important? Why is it important to actually create a graph database instead of a regular RDBMS database, right? So there are some use cases. Let me actually give an example, like a real life example. I'm not going by order. I'm just giving the real life example first before I go into the definitions you're seeing on the screen. Google gives us all the web pages ranked by their order. And how are they ranked? They're actually connected in a graph database with relationships to each web page that is referring to a different web page. With a relationship between those two, they are connected. Each web page become a node, and any web page that is referring to a different web page will have a relationship to the second one. So that's how they are connected in a graph structure. Each web page becomes a node, and if they are referring a different web page or they are referred by a different web page, they'll have a relationship to different nodes on the graph database. And Google uses a rank called PageRank algorithm, and they actually, this is one of the examples of how we can leverage graph databases. So the PageRank algorithm will make count of, like, how many pages are referring to a particular web page, or how many pages are being referred by a web page, and it uses that information to come up with what is the most useful information for an input query that you have given. How does it know? It knows by how many people are referring to that website, or how many people are using that website as a result when they query for it. That's how Google knows, hey, this is a good web page to show for a particular query. That's one of the examples of a graph algorithm we are using, like, in everyday life. Similar to that, not as complex or as complicated, there are like some metrics that we could use in day to day, and there are some which are like a little more complex and would be useful in a corporate setup. The easiest of the metrics in a graph database is, right, how many number of nodes or how many number of edges are there in the graph database. You can consider this as number of rows and number of columns in a RDBMS instance. How, like, when we have to define an RDBMS, like the statistics of it, how we say, like, hey, this database has so and so many rows and so many columns. Similarly, in a graph database, we say, hey, this database has so and so many nodes and so and so many relationships between them. That's the graph level metric to define how big is the graph, basically. And then degree is a metric at the node level. It doesn't it is not a graph level metric, because you don't have like a degree for the entire graph. A degree is applicable for each node, and what it defines is how many number of edges are there to a particular node. In terms of undirected, it doesn't matter whether it is going inside or whether it is going outside, because there is no direction. Any number of edges will define the degree for that particular node. And whereas it comes to directed graphs, you have a direction. So some of the relationships might be coming in and some of the relationships might be going out. So based on the number of relationships that are coming in, that will become an in degree. And the number of edges that are going out of a particular node will become an out degree. And there is distance metric, which is the shortest path between two nodes. And there is this is between the nodes. The distance I'm talking about right now is a distance between two particular nodes. And there is a graph distance as well, which defines what is the longest of all the shortest path between any given two nodes in the graph. So if you take like n number of nodes in a graph, there will be like n into n minus 1 by 2 number of possible relationships between each. And then if you take all of those shortest paths, and if I take like, node 1 and node n, we'll see like what is the shortest path, and we connect it with everything. And then we do the same, we repeat the same for all of the nodes, and we take the longest of those shortest paths as the distance of the graph. And then again, there is graph radius and diameter. And some of them are like summary statistics. You really like may not have, let's say, a real world application or a real world use case for it, but some of them are used every day in everyday life. In fact, especially the next one, the closeness and betweenness centralities, we can look at those definitions and some of the examples that, how is it being used every day. Going back to graph radius and diameter, it's like how far a particular node is from a node the most distant from it. It's exactly like the graph distance, but this doesn't have the limitation of calculating it as the shortest path. That's the diameter of the graph, and obviously the radius is half of it. And then closeness and betweenness centralities are right. These are very interesting metrics. So the closeness is how close a given particular node, and these are metrics at the node level again, how close a given particular node is to the rest of the graph. And how is it useful is, right? Let's take an example of either Instagram or Facebook. Again, if we make all the people as nodes and if we connect them by either followers or by their friendship on Facebook, you will have a network of like, let's say, millions of nodes, and then you will have like a network of people you are connected to and the people they are connected to and the people they are connected to. And we, in the recent times, we have heard like internet celebrities, right? Like Instagram celebrities, and there are like influencers in social media, either on TikTok or Instagram or Facebook, anywhere, right? How are these influencers are decided? This is based on some of these metrics, either closeness or between centrality. Closeness, what it defines is if someone can actually reach the majority of the network with only a few steps, right? Like let's say I am connected to Srinivas Rao and Srinivas Rao is connected to Funny. I can reach Funny with 2 steps, but there is like Srinivas Rao and some of his colleagues can reach Funny directly, right? So we calculate closeness of each node to the rest of the network and see like how many steps does someone has to take to reach the rest of the network. And if someone has less number of steps to take to reach everybody in the network, he is a big influencer. He can reach most of the network without taking many steps. So that guy will become an influencer in a social media connection, like in a network. Similarly, between a centrality is defined by which particular person or which particular node is connected through most of the shortest paths between people. So I might not be connected directly to, like, let's say someone in Pace Institute, but I may be on the shortest path from someone from my company. If they are trying to reach to someone in Pace, their shortest path will go through me because I know or they know me from the company. They can go through me and reach to the Pace in a shortest way compared to the rest of my colleagues who don't have any connection with Pace Institute, right? So I will become important in that network because through me, people can reach some of the network or the entire network in shortest distances. So these people are the ones who can spread. If I take an example of news spreading, right? These people can spread the news very fast, whereas the closeness centrality determines someone who can reach most of the people in less like distance. The between the centrality will define the person who will reach most of the network in shortest of the time. Any questions so far?
So the closeness metric is reaching more number of people in shortest of time, and between the centrality is reaching. What's the difference in the last line of between?
So let me repeat that, right? So the closeness centrality is, right, irrespective of whether you have a shortest distance between like the rest of the network or not, you have a connection that will reach the entire network. And the distance to reach that, like the number of hops you have to make it, is the lowest. Whereas between a centrality, you'll have to determine the shortest paths, right? Like for example, for me to reach you, I might have a connection through, let's say, Pace College, or let's say the HOD of CSC department, right? Mr. Srinivas. So for the shortest path between my node and you is through Srinivas Rao. So Srinivas Rao becomes important there. He is part of our shortest path. Whereas there is a separate network. Let's say I know someone who is working in my company, who knows someone who is working in, let's say, Apple or Facebook, and then they know someone who is your student or who is your student's father or someone. I can reach you, or someone from my company can reach you through that network as well. But that one will take a longer time. that's not the part of the shortest path. In that case, Srini's between centrality will become higher, right? Because the shortest path between someone in my company and you will go through Srini only. So Srini will have more between centrality, because a lot of shortest paths, just like the example I gave, we'll have to calculate the shortest paths for the entire network. By the way, it's not just one path I'm talking about. We calculate the shortest paths between each pair of nodes in the entire network, and whoever is going to, or like whoever is the node that most of the shortest paths are going through, those one will become the most important in terms of between centrality. Whereas the closeness centrality, there is no shortest path concept, right? You are the originator, like the one particular node is the originator, and you calculate the distance between from that node to the rest of the entire network. Am I making any sense, or should I say it in a different way?
Thank you, sir. Thank you, sir.
All right. Any other questions? All right. I take it as no more questions, or should I wait for Funny or Srini, if you are online? Let me know like how long should I wait for a question before I move on.
No, you can proceed. If there is any questions, they will ask. No problem.
All right. Sounds good. Thank you. And then the last line here is a very interesting concept, because this is the power of actually having graph databases. A click, right? A click is a network where, like, for example, if I take my LinkedIn network, and if I have 10 people in my network, a click will form with all of the 10 people if the 10 people inside that network, if each of them are connected to each other completely, right? I'm like, they don't have to go through me, they don't have to go through some other person, but each of those people in that sub network are connected to each other directly. Like if I have taken a subgraph of like 10 people, if each of the node is connected to the rest of the 9 people, it's called a click. It's a complete graph. It's a complete subnetwork. And the reason why this is important is, right, we use this one, and the next term I'm going to define the communities, right? Communities is like, if any of you like are probably most of you are aware of clustering in machine learning in general, right? Community detection is very similar to clustering. What we do is actually we create clusters of communities. The community is a graph theory word, but it's very similar to clusters in machine learning. We create communities to understand, like, you know, who are like relevant to each other and who is different from who, right? And the reason I say that this is very important, again, another real life example, like LinkedIn or Facebook or Twitter, whatever you follow, whatever you use, you see all of these recommendations for friends, right? This is how they actually come up with. They create communities, they run community detection algorithms on the entire database, and they actually come up with these communities. Like, let's say the entire Phase community faculty will become a community, because majority of them will be connected to each other at least. And there might be one person who's not connected to one. And then that's where the recommendations come from. When they identify a community and they see like, hey, this is a very strong community because the community, most of the people within that community are connected to each other. But these people, like, let's say person 1 from person 2 or person 10, they are not connected. They are in the same community, but they are not connected with each other. So we can probably recommend, hey, this, you know, all of you know each other from Pace Institute, and, you know, here is the information. Like, would you want to be connected with the person 10? That's how the recommendations come up. And the click is when that community comes up. Most of the time, the community is not 100%, because I'm only taking an example of like 10 nodes, right? But when in real life, you might have like 500 friends on Facebook. And when they take a community detection algorithm and run it on 500 people, it's unlikely that all 500 of people are connected to each other, right? Like, let's say person 10 might be connected to you, but might not be connected to person 100. But all of them are like in your friends network. And then what happens is that's where the companies use that information to suggest to the person 10, hey, you're not connected to person 100. You're in the same community, like either through Pace or either through data science interest, and you attended the same conference, let's say a while ago. And then, you know, would you like to be connected to this person 100? That's what the recommendations will come up with. And their target is to become to make that community a click. right? Because their target is to connect as many people as they can. When that subnetwork completes, it forms a click. So their target is to reach that click using the community detection algorithms. Any questions on that? Nope. Let's move on. Sorry, go ahead.
Yeah, when node is getting a click, that means that it is moving its subgraph to another subgraph, and they are collaging into a huge graph.
Partially true, but I would not define click in that way. I would say click is right. It doesn't start with one node, right? A click is a subnetwork. It's not just one node, or it's not starting from one node. I only took an example of your Facebook network so that you can relate. But a click is a subnetwork, right? Like, let's say it could be any subnetwork of, let's say, a subnetwork of all the faculty members in PACE, or a subnetwork of all the people who live in like Ongole or Kandakur. By the way, I'm from Kandakur, so I'm taking Kandakur there. So, or probably let's say just Delhi, right? So a subnetwork is it could be any bunch of nodes, right? It doesn't start with a node, but when that bunch of nodes come in, it's likely that all of these are connected, but not every node in that subgraph is connected to each other node in the subgraph, right? Let's say if I take every person in Ongole, Srinivas might be connected with, let's say, someone with the name Ramesh, right? But he might not be connected to someone with the name Naresh, right? Then it's not a direct connection, but they are all in the same community. They all live in Ongole, let's say. When that is a community, when it is detected, but when we connect all of these people with each node connecting to each other node in the graph, that's when it becomes a click.
Right.
I can we will see the networks in a few minutes. I can show you an example of a click, like how does a click look. All right, I'm assuming no more questions. Moving on.
Yeah, you can.
Yeah, here are some tools I wanted to introduce to you guys if anyone is interested. Well, you might not be as interested yet, but I think once we see the example, I am hopeful that at least one of you will be interested in these, and you could try some of these databases and programming languages and visualizations for free. The Amazon Neptune is not free though. ArangoDB, I think they have a test version, and I use Neo4j. Neo4j is the most popular graph database in the enterprises, at least. Their enterprise version is the most popular, and you can use their enterprise version for personal use without any charge. It's free to download. You have all the features except, like, they have a restriction of like a few billion nodes. You can't go beyond few billion nodes, and I think on a personal computer you can never go beyond those limits. So it's easy to download and explore. And then the programming languages, Neo4j developed a programming language called Cypher, and that's what I generally use because I'm using Neo4j. And they made it open source recently. They released the compiler code as well. So it became an open programming language. Previously, it was only like for Neo4j, but now it's an open source programming language. And you can search for like Open Cypher in Google, and you might actually come up with the ways of using it with any other graph databases. If you are using Neo4j, it's natively supported, so you don't have to do anything. And then GraphQL is a query language that Facebook developed, and I'm guessing they are using that internally as well, because as I said, like I've been taking the social networking as an example of connecting people and all that stuff. So they do these networks in their like everyday life, and they use this programming language for it. And then there is a programming language called Gremlin, which is developed by Apache, just like as any programming language or any tools that are developed by Apache. It's an open source programming language. it is licensed for anyone to use, basically. So you could use that as well. And then when it comes to graph visualization, this is the most interesting part. The visuals are very appealing. And Gephi is a Java-based program. Again, it's also free to use. It's a Java-based program which is used to visualize like how are people connected, or like, you can connect like any kind of network, but yeah, it is only for visualization. It doesn't have like many algorithms that you can run, like closeness, centrality, and bitwidth centrality. They might have developed it recently. I've started using Neo4j in the last few years, so I don't know if they have the algorithms now, but it's very good for visualization. And the Neo4j actually delivers a browser and a Bloom software as well. Both of them are free to use, and we'll see the Neo4j browser in a bit. The NetworkX is a package, NetworkX and Snap, both are Python packages if anyone is interested in defining the nodes and relationships programmatically, and then use that for visualization. NetworkX and Snap for Python are very good visualization tools. Do anyone need more information about these tools? I take it as no, and then we move on. So today's example, I am going to actually convert a particular CSV file, right? Like that's how we receive the data, and then we convert that one into a graph database and graph visualization as well. So how the data is stored, right? We get a list of all the pipelines that are connecting like a platform to a platform, or a platform to a subsea unit. A subsea unit is where the oil is being pulled out of the earth, like from the earth of the, not from the earth, from the base of the ocean. Yeah, that's the word I was looking for, from the base of the ocean. So there will be like a platform on top of the water, what we generally see, and we consider it as oil platform in terms of like technical words, and we generally call it oil well. But oil well is something we cannot see generally. It's on the seabed. It's in the it's beneath the ocean, and that's where the oil is being pulled out from, and then it sends the oil to the platform which is on top of the water, and then the oil from the platforms will be sent to a refinery unit. It might actually have a pipeline connecting from one platform to the next platform, and from that platform to the next platform. They connect like that, and then it reaches shore where it gets processed. The crude oil gets processed, and we receive like petrol, diesel from it. So the data what we received, right, are the list of pipelines that are available in the North America. And each row you see here is, right, it's a pipeline. And it goes from like, one platform to either shore, or it might connect to a different pipeline, which is a bigger pipeline. And then that goes to a different platform. So like that, we have a connection of like all the pipelines that are transporting oil. And if you see the from ID to ID that I highlighted here, these are the basically unique identifiers, like in a database. These are the unique identifiers which identify each structure in the network. They say like, hey, there is like platform number 1, which is connected to platform number 2, or which is connected to platform number something else, like that. So we use that information, right? And like for connecting in a graph database or in a network, what we need is nodes and relationships, right? So how do we define nodes is that each of these platform, like either in the from list or in the to list, will become a node, because it's a platform, or it's a pipeline, or it's a pipeline which is a junction. Sorry, it's not a straight pipeline. It's a pipeline which is a junction, or it's a subsea unit, which is like the oil well, which is on the bed of the ocean. So it could be any structure that is a node, and the links between them is the pipeline which is connecting two different structures. And each row here is a relationship which is connecting two structures. That's what we see here. Any questions about the data? Okay, we go from here. This is the data, and we actually create this visualization here. The left network you see here, and especially the center of the network, if you see, the red dot in the center is the processing unit or shore, like where the oil ends up in the end, like finally. And all the green dots connecting around that particular red dot are the platforms which are sending oil to process to this shore. And if you see, some of those platforms are like very close to the shore, and some of them are not. Some of them are like going through multiple steps. Like, it has, if I don't know if you can see my mouse, but if you can, I'm pointing here. So this one here will have to send oil from this platform to this platform, this platform to this platform, this platform to this platform. And, it has to take many steps before it reaches shore. Whereas the platforms which are next to it can send directly to the shore, and because they are very close to the shore, they're not in the middle of the ocean basically. So this is the graph database that we will create from the CSV file that we just saw. And how do we use it is that the visuals of the big network is always interesting to look at, but how do we use it is when we come to like an example like this, right? If there is a platform like with the ID 202801, how is this platform sending oil to shore is something that I want to understand. Whereas in CSV case, right, I'll have to see, hey, in the from ID list, I'll have to see where is the 202801, and then it will have a to destination. And then from there, I'll have to say, hey, where is this going from here? And then I'll have to search for that number in the from list again, and I'll have to see where the to ID is. And then if it's not the shore, and I'll have to take that again, and then see from the from ID, where is oil going from that particular from ID, what is the destination ID. So we'll have to like manually go through multiple rows to see how the oil is being sent from 202801 to the shore. Whereas in here, once you create the graph database, the network, with all the pipelines, all you have to do is just, put it on the visualization, and you can see, hey, from 202801, it's going to a subsea unit, probably it's going to 202802, and from there it's going to some other pipeline. It's going to some other pipeline here, and then it's going to here, and then it's coming here, and it's going to shore. So this is the pipe, this is the path the oil takes to go to the shore. And this one is gas. I know it is gas, that's why I was not taking this example. So the gas, if there is like liquid gas that comes out of this platform, it takes this path to reach either a terminal or shore using this path. If it's oil, it goes this path, because the pipelines can carry only one type of material generally. There are some pipelines which have like sections within them, and one section carries oil, one section carries gas. So there are like some pipelines like that as well. So this is how we can use graph databases instead of like trying to manually review from each node how the oil is being transported to shore. We can create a graph database and we can easily visualize how is it being transferred. Any questions? All right, I take it as no questions. Let's move on to the next one. Here, I'm just introducing, right? I'm like, what is the business problem? What was I trying to do? And then like, how did we do it? How did I define the graph database? And then how I'll also show you the code to create that graph database. So the business problem was to measure the risk of insuring a particular platform or subsea. How do we do that? By estimating the production stop scenarios. Like for example, in the previous case, if an insurance company has to insure this 202801, it has to know if anything like 208978 or 202802 goes down. If that is broken or one of these pipelines is broken, 202801 cannot send oil to the shore. It cannot produce any more oil. So that will have an effect on the revenue of this particular platform. So the insurance company will be in loss basically, and they'll have to like measure this risk of insuring a particular platform to make sure like, how much premium do they charge this particular platform. So that's the business use case. And I will go into more details, but how am I doing it is I am calculating the number of steps oil has to take to reach from the platform to the shore. Like, it has to take like, this particular example, it has to take like 1 step, 2 steps, 3 steps, 4 steps, 5 steps to reach the shore. And the other thing is each of these pipelines will be of different length. right? And like some pipelines are like hundreds of kilometers of length, and some pipelines are just 2 kilometers. Some pipelines are just like less than a kilometer. So there will be like different lengths of kilometers, and the longer the length of the pipeline is the riskier, because it can break at any point in that entire, like let's say 100 kilometers length. So the longer the pipeline, the more riskier it is to ensure that particular platform. So I'm using the length of the platform, the length of the pipeline, and the number of hops or the number of steps oil has to take before it reaches the shore. And I'm also considering, hey, is there an alternative way to send the oil? Like, let's say if there is one line here, and what if this line breaks, right? Like there could be another line that the platform could use to send the oil back. In that case, if there is like alternative routes present, it's less risky for the insurance company to insure, and it's less risky for the production as well, because there is an alternative route. If one goes down, we can the platform can always use the other route to send the oil. So our goal is to identify how many number of alternative routes are there, and what length or what distance oil has to travel to reach the shore, and how many number of stops it has to make before it reaches shore. That's the metrics that we are going to calculate even today. The data we have already seen the pipelines data, and there is like similar data, the metadata, lookup table data for platforms, like, what is the name of the platform, where is it located, what is the material of the platform, like is it steel, is it not steel, is it plastic? I'm like, it's not plastic, but yeah, just examples. So there is like metadata about each of the platforms and oil wells. And the terminal, or an SPM, is the processing unit. That is the destination for oil. A terminal is where the oil, I don't know if you have heard the word oil refineries. If anyone's from chemical background or mechanical background, you might have heard of oil refineries. So our terminal is an oil refinery, and SPM is a place which is similar to terminal, but it doesn't end there. The oil gets transported using ships from SPMs. So there are no more pipelines. The oil gets transported from a ship, like using a ship. So that part we can't really calculate, like, whether they're using a ship or not, and when is it being transported. So as long as it reaches a SPM, we consider it as it reached the destination. For this particular problem, how do we define what is a node and what is an edge, right? This is one of the easiest problems, because we know the nodes are the platforms or the structures, and the edges are the pipelines, because the pipeline in real life is actually connecting to two different locations. So it's an easy answer to say, hey, what is this edge, right? It's a pipeline which is connecting to different structures. And one example is that, so some of these pipelines, right, they might not go directly from one structure to the other structure. They might actually join a different pipeline, which is a longer pipeline. Let's say there is a pipeline between structure 1 and structure 2, and there is structure 3, which is the new one. It has to send the oil to structure 2, but it doesn't have to make the entire pipeline of like 500 kilometers to structure 3, but it can send, it can lay a 100-kilometer pipeline and join the connection between the structure 1 and structure 2. So you can use that pipeline for sending the oil. So in that case, we convert that T junction into a node, so that we can identify, hey, this is the pipeline, or this is joint where a couple of pipelines are merged together. The tools I used for this problem was Neo4j and Cypher programming language. I used Python for automating this entire process, so that I don't have to like run it manually every time we get the new data. Except for that, I think Python has no role to play in the calculations of what I was doing. Any more questions? All right, I take it as no questions again. Sorry, was someone about to say something? All right, before we see problem in the visualization form, I just wanted to give some food for thought. Any problem like we are working on, right? If you are trying to define a graph database, the easiest of the rules to remember is that all the nouns will always become the nodes, and all the verbs become edges. Like, for example, this person married, like Dan married Anne. Dan is a person, it will become a node. Anne is a person, it will become a node. Married is a verb, it becomes a relationship between these two persons. So it's very similar for any use case anyone's working on. Most of the times, more than 95% of the times, the nouns will become nodes and the verbs will become the edges between the nouns. And then if there is like any attributes about this particular noun, it will become the property of that particular node. And those are generally adjectives. Like let's say, 5 feet, 10 inch tall Dan, that's an adjective of the person Dan. So that edge will, height will become a property of this particular node. And then the other noun, let's say any adjective for Anne, like, let's say beautiful bride Anne. So, there is a property like how is she beautiful, something like that, right? That will become a property of the node as well. And if there are any adverbs, those will become the property of the relationship. Like in this case, married on, let's say, particular date, right? Some particular date, that will become that. So this is a simple rule to remember. All the nouns will become nodes, all the verbs will become relationships. Adjectives will become properties of the nouns. Adverbs are, just like in English, adverbs are the properties of verbs. So those will become the properties of relationships in Graph database. All right. I think we are good to go. We can see it in action, how this problem was solved. Any questions before we see the code?
No, sir.
All right, thank you. Thanks for confirming that. It's good to hear. Yeah, I hope I'm not talking to myself. All right. So here is the database I created. As I was saying, like, the node count and the edge count is the easiest of the counts we can say about a graph database. So for this particular data we are talking about, there are like 10,000 nodes and there are about 18,000 relationships between those nodes. And here is the visualization. And as you see, there are like a lot of keys, like properties of the node. If I take any platform here, that one has properties like, whether it is excluded from the network or what is the type of the facility, whether it is a platform or not, and what is the field it is in. And I have like latitude and longitude of the platform as well. And then what is the name of the platform? All of this stuff, like all of the properties of the platform will become the properties of this particular node. So this is the graph database, and how did I create this one is what we look at, right? For today. Let's see. So this is the code I have written for the entire, like for crossing the entire database. But I think before going there, let us actually see this Cypher introduction, right? Like, how do we write Cypher? Cypher is a programming language probably you're seeing for the first time. So I'm going to like write something. I actually did it yesterday. If I want to create like a property, like a person node, right? How do I create it? Is these, the language is very easy, very intuitive to learn eventually, but the first time you see it might be a little tricky, the syntax, but once you get a hold of it, it's very intuitive in a way. All the nodes are identified or represented in parentheses, as you see here. And then any properties are identified or represented in curly braces. And any relationship is represented in square brackets. So that is the basic fundamental rule. All the nodes are represented in parentheses. All the relationships are identified in square brackets, and all the properties are identified in curly braces. So if I have to create a person, right, what I have to do is that I'm going to, I don't know, why do I have it here? But yeah, we can create a new person now. Let's say create a person, right? Create, I can call this as any variable. I am going to call it like v or var that we can all identify. And the person, it's called a label in Neo4j. It identifies what kind of node are we creating.
Can you please zoom it?
I think I can. Let me try here. view, zoom in. Any better? Should I make it even bigger?
Little more, little more.
Yep.
Yeah.
Good.
Yeah. Okay.
All right. I have, I'm trying to create a person node here. So what I'm doing is create is the keyword to create a person. And then because it's a node I'm creating, I use parentheses, and then var is a variable. So I can call it anything. And then anything after this colon will define the type of the node I'm trying to create. Like in terms of my example I was talking about, right? A platform is a type of node, and terminal is a type of node. So I'll have to know what is the source and what is the destination, right? How do I distinguish between a source and a destination? Is using the type of the platform. So the type of the structure. One is a platform and one is a terminal. So similarly, in a, let's say in a Facebook network, right? Each person will become a node, and each page will also become a node. So if I'm creating a page node, this person will become page here. And then I am, let's say I'm creating a name. Funny, I'm going to use your name because I just came to know about you. So I am trying to create a person, and I'm saying the property of that person is the name, and the name is funny. So because properties are like identified in curly braces, I'm using this curly brace here. The name of the property is name, and the value is funny, right? And if there is like, let's say another property for him, let's say occupation, because I've already used it. And occupation is, I don't know whether you're associate or assistant. I'm going to put you as professor. Oh, I'm typing, but it's not responding. Okay. So I'm putting you as professor. So if I execute this one, it'll create a node. And then one thing to remember is, right, graph databases are schemaless, like unlike the RDBMS where you'll have to define the schema, like, hey, what is the name of each column, what is the type of it, and what is the maximum length for it. We don't have to define anything in graph database. It's a schemaless design. I can create a node today. I can create a node like after 100 years. I can create a different type of node, and I can still connect. Let's say I create a page type node tomorrow when I realize, hey, my problem needs pages as well. I create a page type node, and then I can connect person and node. And the properties of a person, right? Right now here, I used both like name and occupation for each of the persons. And let's say if there is a person who doesn't have occupation information, we don't have to provide it. It's okay. It doesn't matter. You can only provide what is the information you have. That's it. Because it's schemaless, it doesn't give you execution errors like, hey, you can't put null for this particular column or something like that, unless you use it as an ID, as a primary key, just like in RDBMS. If you use it as a primary key, you can't make it null. So this particular row will create funny node. And I know that funny knows Srinivas Rao. So I will say, like any person, right? Let's call it Sri is a person with the name Dr. Srinivas Rao. And this is a node. And I also know another person, right? So I'm actually filling this mid part later. I'm actually trying to make it as simple as we can, right? So we are trying to create a relationship between this particular node and the other node is funny. That's just a variable name. I can call it anything. It's a person type node, and then the name is funny. I'm using funny here as the primary key, as the identifier to identify that particular node. So I am trying to connect to these two people. So what I do is, hey, this is the person, and I need to connect them. When connecting, what happens is, all you have to remember is a direction, like who is connected to who. And this particular connection is, though it is undirected, Neo4j uses everything as directed connections. The reason for that is for optimization. When it knows the direction, it's easy to traverse, right? I mean, like in case of undirected, you don't have to even worry about which direction it is going. In your queries, you just say no direction. That's all. But it's faster or optimized to connect. So this is a relationship. I connect person Srinivasrao to person Funny. And if I want to call that relationship something, I provide that information in this square brackets. And then we call it, what do I call? Is a colleague again, of course. Is a colleague. So if I execute this one, I am connecting Dr. Srinivasrao to Funny. And one interesting fact about Cypher, right? I don't have to execute all of this before I execute this one. If I execute this one particular line, it will actually create a person node with the name Srinivasarao, and it will create a person node with Funny, and then it creates a relationship as well, which is between those two. So with one line of code, I can create all two nodes and a relationship between them, all without without like creating them manually. That's the syntax of Cypher. Any questions before I show you like what is the code I have written?
So one question.
Sure.
Sir, in the sixth line, you haven't written R there for the relationship. Do we always have to write R?
So this is a variable name. If you want to use R is just a variable name. So anything goes before the colon, right? That is a variable name. And if you want to use, like, if you want to set any properties for this R, right? Like, for example, if you see here, my example, like my code example here, I am going to use this variable name like structure from to set some other properties in the later statements. You only need a variable name if you are going to use that in the later statements. If not, you don't have to do it.
Okay, sir. Thank you.
Yeah, sure. All right. I am moving on. If anyone is interested to know what is the IDE I'm using, this code editor is called a VS Code, Microsoft VS Code. They have like language support for more than 100 languages if I'm saying it right. And there is the Cypher query language is the Cypher syntax highlighting. That's why you see all the colors here because they have the highlighting. So these are the samplers, and here I am using the pipelines data that we just saw in the presentation, like, how a pipeline is coming from one structure going to another structure. I'm using that information. I am creating, so the syntax for it is, right, load CSV and all of these syntax, like, to read the data from each line. So it reads each line as line. And the terminator in the file is a pipe delimiter. So I use that one there. And with each line, what I do is, right, I first create a from node. And if you see here, instead of create, I am using merge. The reason for that is merge is like a statement which is create and update. So it's a single statement to do. If there is no node present, it creates the node. If there is a node already present, it will only update the properties of it. And if the properties are already the same, it doesn't matter. If there is no update you want to do, you can ignore this part as well. So merge is like a foolproof statement to create nodes and relationships, so that you don't have to worry whether this is a primary key, and if it's already present with the structure ID, is it going to throw an error? You don't have to worry about it, because if it's already there, it doesn't do anything. So what I have to do, right, from each file, I'm going to actually show you the file. So you have the file here, right? From ID to ID, I have all of these columns. I'm going to select those columns from this each line, like, the from ID and the from structure and the to ID and the to structure. And for each of those structures, I am creating a node here with some of the properties, like, hey, what is the type of the structure, what is the facility type, and what is the field number for the particular platform or subsea unit. And then I do that. And then in this query, I write a relationship between those two. If you see, the relationship between these two persons is very simple, right? I'm like, all you have to do is just R is equal to, that's all you need to write to create a relationship. But I'm doing more here. The reason for that is, if you notice this entire part from here, I am trying to see here, these are all properties of that pipeline. These are all optional. Either you want to use the properties or you don't want to use the properties. If you want to use the properties, you define all the properties inside the curly braces, as we just talked about, right? And if there are multiple properties, you separate them by comma. And then you create, like, what all you are doing is, right, you are creating the structure from variable here, which is the from ID. You are creating the structure to ID here, which is from to ID. And then you are connecting structure from and structure to. And I'm going from to, as you can see the arrow mark here. I'm going from to. This pipeline has, some of the properties, so I just created those properties here. And for some of the properties, I did a transformation, right? I mean, just like in SQL, if I want to use a case line statement, case when statement, and say, hey, when the type of or the status of it is like firm plan, use it, or if not, don't use it, something like that. If you want to do the transformations, you do all of them after you create the relationship using a set statement. And I repeated the same process for the pipelines, for the platforms. The platforms is, again, it's all just the properties of the node. And I did all of it. I executed this code to create this particular database. Any questions, or if anyone wants to see the details of the query, please do let me know.
Structure from and structure to are nodes, and properties of the relationship. That is the
yes, and structure from and structure to nodes also have some properties, but when I created those properties when I'm creating the nodes. If you see here, right, I'm creating a from node. So this is a node, as you said, that's right. And I'm also having some properties for this node. Like, I'm saying, like, what type of structure is it? The structure type is the property name. And I'm also saying what is the type of the facility where the structure is. And we also have properties for relationships. So the connects to is the relationship name. So I'm just saying the structure from connects to this particular structure. And what does that pipeline have is all of these. Like, I'm saying, like, what kind of oil or gas does the pipeline contain or transport, or what is the status of the pipeline? Some of the pipelines are already broken and we can't use it in the data anymore, right? It's not operational or it's not installed yet, so we can't use them. So I'm just marking them on the pipeline and saying, hey, this pipeline is broken, or this pipeline contains only or carries only gas and oil, or it carries the gas, oil, and condensate as well. There are some pipelines which actually do water injection only. Water injection is a pipeline which will boost the platform's performance. So there are properties for both nodes and relationships. I hope I answered your question.
Thank you.
Yep. Any other questions? All right, I take it as no, and I am going through all of the code that I have run for creating the database. And then I cleaned up something until here. This is all like for creating the data and removing some, same node to same node relationships within the database. And from there, going back, revisiting the business problem, right? The business problem was to identify how risky is it for an insurance company to insure a particular platform, and how are we doing it? We are trying to see how many number of hops are required for that platform to reach the endpoint, a terminal or a shore. That's one query we'll have to see like, hey, how many number of hops does it have to take? And then the other query is like, what is the distance between that particular platform and an endpoint? And then there is the third point that we were considering is the number of alternative routes, whether there is number of alternative routes are there or not. That's those are the three metrics that we are using to say how risky it is to insure a particular platform. So I am going to dig a little more deep into this query so that we understand like why are we writing this particular query to see what are the number of hops, right? So first thing is that a match is like select statement in SQL. So a match doesn't do much. It just selects data from tables. And then I am creating a variable called paths. You can call it anything. I'm calling it paths. And there is a function within Neo4j Cipher, which is called all shortest paths. What it does is, when we were defining, we were looking at the shortest paths, right? I'm like, we want to identify what is the shortest path from a platform to a particular endpoint, like a shore or terminal. And I am calculating all shortest paths using that function here. And I am starting from N1, going to N2. And this 1 to 10 here determines how many steps can that particular path take. If we are taking more than 10 steps, it's not the optimized way. And I also had to do this because I'm running it on my local computer. If you have more computing power, you could use n number of steps. And just like how it explodes, right? In social network, like if I start with one particular node and I say like, I explore what are the connections of that particular node, I might have like 500 friends. And I take one step and I have 500 nodes to look at. And then if I take the second step from all of those 500 nodes, each person might have like another 500 friends, and it will become 500 into 500 number of steps that I'll have to take. I'm guessing it's 250,000. So you'll have to take as many steps or as many nodes. You have to inspect as many nodes. If you go like beyond 2 steps or 3 steps, that's what happens. But this is pipelines data, so I could go up to 10 steps, and I'm only seeing, hey, look up to 10 steps and see if you can reach a destination from the starting point. All I'm doing in the first row is I'm saying, hey, there is node N1. It has to reach node N2 within 10 steps. That's all I'm saying. But I'll have to have some where conditions, right? I'll have to say what is the N1 and what is the N2. I am saying N1 should be either a platform or a subsea, because that is the starting point. That's where the oil is being produced. And then, and then I'm making sure that the status of it is not excluded. We excluded some of the platforms if they were shut down, if they are not anymore in use. We don't have to calculate that, and we don't have to use it. So I'm saying, hey, N1, and the colon, as I said, like, this is the label of the node. We were defining like persons. Similarly, we use platforms and subseas. Anytime you see a colon, it's defining a label in the database. So the starting point should be a platform or a subsea, and the endpoint is an endpoint. I labeled all of the endpoints like terminals and shore as endpoints. So I could use just one label, say, hey, N2 should be an endpoint, and it's not excluded, right? So this part defines what is the starting and what is the ending point. And in between those 10 steps, I'll have to make sure, if I'm looking at an oil path, right, the pipeline that I'm looking at should be carrying or should be ready to carry liquid oil, right? So that's why I am making sure that each leg in the relationship of this path is not excluded, and it also carries a product which is either oil or oil condensate, like anything that carries oil, basically. So this particular condition is making sure that when I'm calculating a path, the path only is talking about the oil carrying pipelines. It's not going somewhere else. Like, it's not talking about water injection pipelines. It's not talking about chemical injection pipelines, or it's not even talking about just the gas pipelines, right? There are some pipelines which only carry gas. That's what this one is doing. And then here, this particular part, I am what I'm saying here is, right, this particular AND condition, I'm making sure each pipeline, which is each relationship, is carrying the product that we are interested in. And this where condition, what it is doing is, it is looking at all of the nodes of the path, excluding the first one and excluding the last one. The 1 and -1 are the starting point and end points. So I'm excluding those two, but every other node in the path should be either a platform or a subsea or a pipeline. So the reason we make sure it is this, right? I'm like, there are some pipelines or there are some connections which is going out of a terminal, and we are not worried about it, because once we reach a terminal, we reach the destination and we don't have to worry about what is beyond a terminal. So our path should start with a platform and should end with a terminal or whatever the endpoint, right? So I'm just making sure all the nodes within that path are either platforms or subseas and pipelines. That's all. And then return is like, again, select statement, but returning the results or putting it on the display basically. So I am saying N1, whatever is here, right? That N1.structure ID as the starting point where it is being started from. And then I'm actually calculating the minimum of the length of the paths, because there could be multiple paths that our platform could use to reach a destination, but I'm using the minimum of it to say, hey, this is the shortest path for this particular platform. And then I'm also using the number of nodes in it as the nodes in line. So this one is calculating the pipelines in it, and this one is calculating the nodes in it. I am doing -2 because I want to exclude the starting point and ending point. I only want to use the middle hops as the number of nodes in line. And the last is something similar, but I don't calculate pipeline as a hop here. I only calculate if it's a platform or a subsea, and you don't have to worry about all these details. But the one thing that we need to know is, right, it's the number of hops that are required, and we are doing that using here, either using the pipelines or using the number of nodes in the structure. And I executed this query already, but we can see it in action if you want to do it enough. So this is the query I just ran. I'm going to run it again. Okay, I don't want to erase that result. So in case it takes more time, I'm going to run it here, and we'll see for each of the platforms how many number of steps does it have to take to reach the destination. So this is the return statement, right? If you see the return statement, the return statement is returning N1.structure ID as a starting point. So this is the starting point. This is the platform ID. And the number of pipes, this is the pipes in line. So I'm calculating the length of the path. That is this, and the number of nodes in line. Sometimes the platform can reach the target or the destination without any platforms in between. Just like what we saw in the bigger network, there are some which are directly connected to the shore. So those ones don't need any nodes or any hops in between. So they can directly connect from the platform to the shore. And then I just count the number of hops, as I said. So that's the result. So this is one metric that we could use to say, hey, how risky is it to, let's say this particular one, right? This one only has one pipeline in between, whereas this particular platform has to take 5 steps. It has to go through 5 pipelines to reach the destination. So it's more risky to ensure this particular platform compared to this one. So that's how we calculate the risk. And I have written 2 similar queries. One to calculate the distance along the pipeline. I add what is the length of each pipeline along the path, so that we know what is the maximum distance that it goes through to reach the destination. And another query to say how many alternative routes are there from the starting point. So there are some this particular example, it has 2 alternatives to reach the shore. This one has 3 alternative routes. If it has more than 1 alternative route, right, it's safer to ensure that particular start point, because if one of the pipelines is down, the platform can always use the second pipeline to transport the oil. Any questions, or anyone is interested in looking at the code for either of these 2?
Yeah, my question is 3 metrics we are seeing: number of hops, the number of alternate routes, and the length of the pipeline. So,
right.
When the number of hops is less, it is less risky, and it is preferable. Similarly, when the length of the pipeline is less, it is preferable. But when the number of alternate routes are more, it is preferable. Am I right?
Right, that's right.
So the risk factor is positively linked with the number of
alternative
routes, and negatively correlated with the number of hops and the length of the pipeline.
That's right. That's right. So yeah, I was not planning on discussing the end result of this, but what we have done, right? The end result we have given to the client, right? We created weights for each of these three metrics, and this alternative routes, right? Based on the value, like 0 to let's say 10, we actually gave it some weight, which is negatively correlated with this. Like if it's 0 or if it's 1. Oh, sorry, this is positive, right? So alternative routes is positive. I'm sorry. If it's 0 or 1, it only gets like 2 points, and if it's 2 or more, it gets like 3 points. So we gave it like some points like that, and we have points for this metric. And whereas it comes to the distance, we actually created sections. Like if it's less than 50 kilometers, it gets more points, like it gets 10 points, let's say. And if it's between 50 and 100, it gets 8 points. If it's more than 100, it gets 6 points. So we created a point system, which is by weight. We created that, and we sum up all these three numbers, and we give it as a risk score for the client. It's a very good question. Did I answer your question, or were you actually going somewhere using that example?
Thank you. Because statistics is behind it. So this programming is bringing to the stats. Fantastic.
Right, it is. Yeah, so I was actually talking about the Python program, right? So this one I have written for this particular presentation purpose, but this is the actual program we gave client, and this is all Python code. But if you see, like, this entire orange thing you see here is the Cypher code. So I have executed Cypher code through Python package. So I create the database, I do everything, and then when I go to create metrics, no, it's not that. I am just trying to look at the final code, right? Yeah, if you see this one, right, the hops in line has some value. I give, like, if it's less than 2, I give it 10 points. If it's 2, I give it 8 points, and all of this. And the distance, as I said, like, if it's less than 100 kilometers, it gets all 10 points. And if it's 100 to 200, it goes in decreasing order. And then there is a critical points, which is the extension of the third metric we were looking at. I didn't present this one because it's not needed, and it takes a lot of Python code rather than Cypher, so I didn't talk about it. But yeah, we create all of these, and we have like metrics that we created. We initially had like some weight, like 1.5 for, or at least you can say 15%, 30%, 15%, and 40% for each of the metrics. And then that's how the 100% of the score is calculated. And eventually we had to like simplify it using 2 variables only. And then we did 50-50 weight. Thank you. I don't know who spoke, but yeah, good question. Any other questions, guys? I'm going to finish my presentation sooner than I expected. I think I was accounting for more questions though. All right. Now that we have seen this code, I'm just going to show one example where we can visually inspect and see, hey, how is this like connected to the shore, and how is it like, transporting oil or transporting gas, and number of alternative routes if there are any, and then we can see all of that. So this is a query I have written, and it's called Ego Network. I don't know if anyone of you heard this word before. Ego Network is a network that is surrounded, it's one particular node surrounded by its network, basically. And if you're talking about like LinkedIn or Facebook, an ego network is all of the connections a particular person or you have. Like, your ego network will constitute the relationships you have, all the people who are connected to you, and the pages you are following, and the number of likes or the likes and comments, whatever you make. So the ego network is all about one particular node, or it's all about you, basically. So right now, what I'm looking at is I am trying to look at a platform, and I wanted to see like, what are the incoming pipelines to it and what are the outgoing pipelines from it, and see how does it reach the shore basically. And because of the limitation, as I said, I was using only like up to 5 steps, because if it's more than that, the visualization will take forever. It never finishes basically. So I'm using like 1 to 5 steps, and luckily for this particular platform, we'll reach shore within 5 steps. And then I am going to show you the graph. I think I've been talking about graph, but I didn't show you the graph itself. We have written the query which gives us tabular data. So again, I have executed that query already. I'm going to just see the result or show that result of that particular one right here. I don't know if you can see this. Yeah, the details are here. The 202.801 is the E2 network I is building on. So I was looking at like up to 5 connections incoming and up to 5 connections outgoing to see how the oil or gas is coming to this platform and how is it going out of this platform, how is it reaching the shore, and all that stuff. I am going to ask Funny, sorry for the pause. Funny, can you see if you can clear this whiteboard? Like all these yellow lines, is it possible?
Yeah.
Is it possible? Yeah. Sure.
So Funny is not available.
It's not doable. Oh, Funny is not available. Okay. Yeah, Shrinu, can you check if you can erase these lines, or it's too technical for us? Is it too technical for us, or can we? Okay. There is a disable annotation for others. I should have done that in the beginning. Hi, names for annotators. Okay. No, I don't think now I can do it. All right. So yeah, here is the back to the topic. Here is the platform that I created the query for, and I'm seeing like up to 5 steps of connections that are incoming and outgoing. And the incoming steps, as you can see, right? I'm like, if this 202.801 is a platform, it is a platform because it's in green color. This is a platform which is floating on the water, and it actually gets connected to more subsea units under the sea, which are actually pulling the oil. All of these nodes you're seeing here are the subsea units which are doing the drilling and pulling the crude oil out. So each of these wells, they pull the oil out and they send it to like another connected subsea unit, and then from there to the connected. This is called a joint, or this is called a piled subsea unit, and then what it does is it sends the oil to the platform. And as you can see, the oil gas pipeline here, there are 2 different pipelines here that takes oil to the same platform, and oil from here goes to this particular platform. And then if you follow this oil network, it goes here, here, and then here to the shore. This is how the oil is being transported from this 202.801, from 202.801 to 202.802, and then a pipeline joint, and then 209.101, and then a pipeline joint, and goes to the shore. That's the number of steps it has to take to send the oil to shore. And then if there is like, as you can see here, the subsea units are sending either oil or gas. So if there is any any gas that is coming to 202.801, the gas will take a different route. It goes from 202.801 to 208.978, and then it goes to a pipeline joint, and then it goes to shore, or actually it doesn't go to shore because this is oil. The gas goes from 208.978 to the terminal for processing. So that's how it is. So if I'm doing the calculation that I was doing for this particular platform, right, I will see like the number of hops is here, like, 1, if I don't calculate the pipeline joints, it's 1, 2, 3. It takes like 3 hops to reach the shore for oil. And if it's for gas, it only takes 2 hops from here to here, and here to here, 2 hops. And the kilometers, the length along it, because the oil has so much length, I'm going to look at the gas. So the gas pipeline, if I highlight it here on the bottom of the screen, you can see all the properties of the pipeline. And one of those is a length. I'm trying to see that one. Oh yeah, here. The length in kilometers, it's 73.75 for this pipeline. And then for this one, it is 139 kilometers. So for gas from 202.801 to the destination, the distance it has to travel is 139 plus 73 kilometers. So it's about 210 kilometers, let's say. That's the length the gas has to travel to reach up endpoint. And for gas, it doesn't have, actually, I was about to say it doesn't have alternative routes, but it seems it might actually have, because I see gas can go this way, and then here is a gas condensate, and from here also it can go to this gas condensate, and from here, if it has another connection to a different terminal, not this one but another different terminal, it can go from there as well. But at least for oil, I think it has at least two alternative routes. One is going through this one, and then as we saw, this particular pipeline, and from here it can go this 202.802 and this pipeline in 209.101, and then directly to the shore. Or it can go this pipeline as well. If you can see, it can go take this route, go to 209.662, don't even touch the 202.802, go to 209.662 and reach 209.101. So even if this 202.802 is down, the production will still continue because it has an alternative route to go through this route. So it's less risky to ensure this particular platform because it has an alternative route. And the overall score, as I said, like if we count the length of it or this length of it, and then the number of hops it takes and the number of alternative routes it has, we might end up with some score, the risk score for that particular platform. Yeah, the most interesting part about the graph networks I see is these visualizations, which are really beautiful to just look at and visually inspect and see, like, you know, how it is connected. Any questions on that? Yeah, if anyone is trying to use Neo4j and experiment, they actually give a sample database. You can do that. And in the Neo4j browser, if you want to like play with the visualization, you can actually, like, let's say, I'm just going to mess up this visualization right now. So if you want to see, like, from this particular node, you want to see all the connections it has, you can click on that node and you can expand the connections of it, and it will show, like, you know, where else is it getting the oil and gas from, and where is it going. You can expand like as many as you want, and you can, you know, go investigate like further as well. So you can always like play around with the visualization. And I'm like, if I have to do the same thing using SQL, I'll have to first write a query to say, like, you know, hey, this is the from ID, where are the two IDs? And you might get like, let's say 3 or 4 two IDs. And from the, you'll have to write another SQL query to say, hey, from this from ID, where are the two IDs? And then for each step you're doing, you'll have to write a self join and another level of query in SQL. But whereas it comes to graph database, all you have to do is just click on it and see, hey, where else is it going from here? That's all you have to do. Any questions on the visualization? And then, yeah, of course, you can change the colors of each label. I put all the platforms in green color, all the endpoints in red colors, and all the pipelines in blue color, these pipeline nodes, and the shore, actually shore is an endpoint, so it becomes red, and all the subseas in some kind of beige color.
Based on the best, shortest route, can we see a thicker linking line, like weighted, in the case of weighted matrix based on degree, and the best solution for our problem? Can we visually see the shortest least number of hops and more number of alternate paths and shorter length? So like that, can be visualized here. There are more options are there, and all the length, the lines, linking lines are similar. Final suggestion of what is the best solution for this problem?
Right. A very good question. In fact, actually, I would be wondering myself, what is the best way to visualize it, right? Unfortunately, on the browser, you cannot do it, but Neo4j actually comes with a visualization tool called Bloom. I was thinking I could open it, but I cannot open it because it will take, the first time you open it, it will take some time to create. But that one, the Bloom, has a position to, or has a place to create formulas so that you can visualize, or you can make the color and the size of the relationship based on the formula. Basically, like sometimes you can say like, hey, if the length is like, if the length of the pipeline is greater than 50 kilometers, mark it as, a red color or something, or mark it green color, or make it a thicker line. You can do that in the Bloom visualization, but the browser does not have as much functionality. One reason for that is Bloom was a paid service until a few months ago. Neo4j actually gave more functionality to the Bloom visualization because it's commercial. But recently they actually made it public. So now you have the same functionality, but you'll have to open Bloom for it. Not on the browser though. Yeah, but it's a very good question. That's what I would do if I am like visually presenting to someone. Well, for our client, we are only using graph database as a method of calculating all of the metrics we are calculating. At the end of the day, the insurance company is only interested in knowing how risky is it, right? So they don't have to see it. They just have to like know what is the risk of it. But yeah, for most of the other projects, we do the visualization, but we use Bloom for it.
Thank you.
No, thank you. That was an interesting question. All right. If no other questions, let's go back to our presentation. All I'm left to present is what other use cases could we use graph databases for? And I think majority of these, I and my team. So basically, I said I'm a manager of analytics, and I have a team of like 6 data scientists, and our team is specialized in doing graph analytics and entity resolution and deep learning. So some of these examples we have done ourselves in our work, especially the first one, like the fraud detection and analytics, right? We have done a financial fraud use case where we connect all the people and their addresses, their phone numbers, and their identifiers, like let's say driver's license number, or we have just like Aadhaar card in India, we have a social security number in US, and there is a similar number called RFC in Mexico. So we were working on a Mexico client, so we used RFCs, and then we connect all of their identifiers to know, like, if the person is the same person, right? If we have a RFC, which is a node, and we say like, hey, this person has this RFC, and if we identify some other person also used that RFC or that same Aadhaar card number, let's say, we know that these people are either the same or they're trying to impersonate each other. So that's a way of like identifying if someone's trying to mimic identification of other people. So we did that for financial fraud. That's one of the use cases we used. And then I know that IT teams can use like network and database infrastructure monitoring. I'm just trying to give an example. Let's say there is a big data network connected with all the nodes in a company, right? Let's say there are 100 personal computers, like 100 people use, and all of those are connected as a big data network, and we can see if something comes online or something goes offline, and we can see like who are they connected to. If they are like one of them are down, how can we reroute any of the workload to anything else? Something like that we could use for monitoring those network and database infrastructure in a company. And then recommendation systems and engineers is the one we are using almost every day. I think Netflix uses a graph database, and Netflix actually made it very popular. They created a Kaggle competition a while ago to see like, hey, can you recommend better movies for Netflix users? And it became very popular. And a lot of those solutions use graph database. Each of the movie will become a node. Each of the users will become a node. And let's say if I am a user, or like let's say I'm a movie, and then 10 users watch this particular movie, and I look at all of these 10 users and I'll see like what are the other movies 9 of them are connected to, and the 10th person is not connected, and then we can recommend that 10th movie to this 10th person, or that second movie to this 10th person, sorry. So that's how the recommendation engines make use of graph databases. And actually every big company we know, like Netflix, Amazon, Google web pages, I was talking about page ranks, right? They use graph databases as well. But well, they might not use graph databases, but they use graph theory, and they might calculate it programmatically. Instead of storing the entire data in a graph database, they might store it in RDBMS, but load it into a graph frame using programming like Spark, and then calculate the values. I said Spark because it can be parallelized, and for something like Google, it has to be parallel. And they can't rely on a database for it. They have to make calculations in memory. And then crime prediction. I actually did a crime prediction project when I was in masters. I was trying to predict the number of, let's say, narcotics cases that might happen in a particular location in Chicago at a given time. And we did normal machine learning prediction, and then we converted it into a graph database problem. We connected all the locations which are next to each other, and then we connected locations where the crime happens at the same time, to see, like, to leverage that information, that, hey, if there is a crime happening in this location, 90% of the time there is a crime happening in a different location in Chicago. So you might actually want to keep an eye on that. So we used graph databases for crime prediction. And then healthcare analytics is one of the best use cases. All the patients will become nodes, and all the diseases will become nodes. You can connect all the patients to their past diseases, and based on the communities that we were talking about, right, in the community, using the community detection, we can see, hey, all of these 100 patients will fall into the same community, and 80 of those patients had, let's say, so and so disease in the past, but 20 people did not have. So is it likely for these 20 people to get that disease? So healthcare companies like hospitals and insurance networks, insurance companies, they are using this information today to provide preventive healthcare, which means that they will give like preventive medicine even before the people are affected with the disease, based on the likelihood of them being affected by the disease. And I'm actually working on a project right now. I am connecting all the patients, and I am trying to see a similar information, right? I'm actually making it more specific. I will see within a community, let's say someone, like, let's say all the people had fever, and if some of the doctors gave like someone dolo and someone gave the other patients $0, and we want to see, like, why are these doctors suggesting dolo and why are these doctors suggesting $0, and what if those patients get readmitted soon enough. So we are just trying to see, like, what are the differences between the medications, and I'm actually working on that using a graph database even today, in fact. That's another interesting example. And then there are knowledge graphs. A very good example is Wikipedia. If you go to Wikipedia, you might see in a any article, right? Any article is a node basically, and you see like some of the other keywords will be highlighted, and you click on that, it will take you to another article. All of those are nodes basically. Each article is a node, and there are relationships within an article which will connect like one page to the other page, and that becomes like a network of all the documents. And knowledge graphs in general are actually created to answer questions basically. We are working on an example. We mine all the news articles on the internet, and then we create a graph database of where did an incident, like let's say there is a cyclone somewhere. We identify like where was the cyclone, what is the location, what is the wind speed, what is the what are the locations that are affected, and how many people died or something like that. And then once we create this information from each of the cyclones that happened, and if there are like locations that are connected between like two different cyclones, we can see what other locations from the second cyclone could be affected that was not already affected in the second cyclone, but it was already affected in the first cyclone, and we know it because it's already connected. So we could use that knowledge graph to answer questions like that. These are some of the use cases. There are like many more. These are just some use cases that I could think of, and I put it on the slides. And that's it for the day. Oh, okay. We are only, I think it's only 5 minutes left for the presentation, and I think we are on time. I'll leave the last 5 minutes for questions. Any questions in general about the slides or about the presentation or about the hands-on machine learning workshop tomorrow.
So in general, we have supervised learning and unsupervised learning. We use a decision tree as a supervised learning technique. So can we use a decision tree for classifying the nodes, that is the platforms and terminal, so that we can group the best or most risky and least risky platforms? Can we use a technique? So what general statistical technique you use for inference?
Sure. I'm going to take it in two different sections. One is that, right, network analytics, majority of the time, will become a descriptive analytic, but not a predictive analytics, solution. Even today, if you see that, right, there is nothing predictive about it, but it is descriptive because we are answering questions based on what happened in the past, right? So that is most of the time the network visualizations or network analytics will become descriptive analytics. But your question is a very interesting question. Can it become a predictive analytic? So network analytics are used are used for feature engineering in a machine learning algorithm. Let's say, for example, I have a classification problem, just like what you described, right? I have all the platforms, and I have like labeled data because it's supervised. Let's say I have all the labeled data, and some of those are labeled as high risky, and some of them are labeled as low risky. And now if I'm trying to predict, let's say out of 10,000 platforms, I have labeled data for 5,000, and for the next 5,000, I'm trying to predict whether a platform is high risky or low risky. Right? What all the information I have until now is whatever is the data that is present on the platform's file, right? I'm like, I might have what type of material the platform is, how many kinds of, probably I can calculate like a statistical measure using like how many pipelines are connected from that particular, using this one, right? Using the starting ID, I can calculate these measures. But what happens is, if I know that, I might get some prediction, but if I use more inferences like from the network analytics, if I say, hey, how many number of hops does it have to go through like the metrics that I have created, right? The 3 metrics that we used, we could use those as features, which will have like more information about that particular node. And I'm thinking, because that's what we used as our expert model, I'm thinking if there are like more number of hops, most of those platforms might have been high risky. And if the length of it is more, and it could be high risky, most of it. So that information will help the decision tree or any other supervised learning model to predict more accurately, rather than having just the type of the platform or the material of the platform or the whether it is oil or gas, that information. Now we have additional information that is possible from that platform. So people do use, and even our team uses graph analytics or network theory for creating more features that that will help you like predict better in a supervised learning setting.
So it's basically the feature extraction that will help you in the prediction.
In the machine learning, yes, yeah. Network analytics itself is not supervised. Is not predictive analytics. It's a descriptive analytic technique.
Thank you. I
But
thought
it's a very good question.
finally, for the oil companies, their clients, they want to have a prescriptive analytics so that they will avoid risky situations prior to happening of any untoward instance. So maybe after the descriptive and predictive, maybe the analytics can prescribe certain insights for the company to take steps so that they can minimize the risky platforms and maximize the more less risky platforms. I think.
Right, exactly. Yeah, exactly. So in other terms, right, the model, whatever I have created, not the queries we have seen today, but the weighted risk score that we are creating, it's called an expert prediction model because we are using the past information, but we're also saying, hey, based on the past performance, this particular platform is more risky in the future as well. So it's kind of an expert model. It's not a statistical predictive model, but it's an expert predictive model.
Thank you very much.
Sure. Good question. All right, we are at the top of the hour. I think we should call it a day. I don't want to steal from your half an hour break before you join the next session. But for tomorrow's session, if anyone is interested in executing the code, please bring laptops or any desktop. If you're logging in from a desktop, now make yourself available on a desktop or laptop. And the data set I've used is public data. I can share the link with you so that you can download the data and we can write the code together.
Okay.
All right, that's all for the day from my side. Funny, Srinu, is there anything that I can do or we're good?
Yes, sir.
Hey,
Sir,
Funny,
for
is there
tomorrow-
anything?
Sir, for
Sorry, go ahead.
tomorrow's session, whether we have to install any software in our laptop, sir?
Very good question. So bring the laptop and let me actually show you. I'm sorry, folks, if anyone has to drop off, you can drop off. I'm just going to show you like what we need for tomorrow's meeting. If you have a laptop, please download this Anaconda Python distribution. Anaconda Python. Yeah, if you just Google Anaconda Python, it'll come here. You can just download this one. And what it is basically Python interpreter, and with some of the packages that we'll be using tomorrow. One is scikit-learn. Scikit-learn is a package which has all the machine learning algorithms in Python implemented. Pandas is a data frame package which is used to store the data like tables in SQL. And then we'll use NumPy, which is all numerical and statistical. Basically, it's numeric Python, which is like all the algorithmic calculations on data, basically. So all of these will come if you download this Anaconda Python. So go ahead and download this one. I already have this one, so I might not be able to show it tomorrow. I already have it installed. So if anyone is interested, go get Anaconda. You could use this Anaconda navigation as well. All we need is a Jupyter notebook for tomorrow, and we can launch it from the Anaconda navigator. I think that's all we have. I'll share the link for the data to download tomorrow, or actually I can share it now. I don't know if it will be helpful if I share it now. Yeah, it's somewhere here. It's a Kaggle data set. It's called the diabetic patient readmission. If you search for that data set on Kaggle, you might find it. We can download it tomorrow as well. I can give you some time to download that data. All right. Thank you, everyone. Thanks for giving me this time. I'll see, if not all of you, most of you tomorrow.
Thank you very much. Very interesting session. Learned a lot about network and graph theory. Thanks for the wonderful interaction. Thank you very much. See you tomorrow.
Thank you so much. It's been my pleasure.
Sir, thank you.
Thank you. Thank you, everyone. You have a good rest of the day.
Yeah, thank you, Sudhir.
Thank you, sir.
Yeah, thank you, everyone.
Yeah. Yeah, dear participants, it is the time to close the morning session. We'll join again at 2 p.m.
Tomorrow you should be managed.
Yeah, afternoon I will explain. Srinivas said,
Okay.
yeah, afternoon, a closing session, I will tell that.
Okay. Thank you.